这个灯不打了。Hello, ladies and gentlemen. It's Alice and from Beijing, and I'm so glad to meet you. I can access talks this Friday. I think that's really a big day because today we're going to have a lot of things on the stage, and today is really, really interesting. We will have the speakers, from a different place, and all of them are superstar. So it's the first time we have two female scientists, on the same stage. I can act talks. Evelyn Wang and Mona Jeriha. Yeah, they're going to have their talks in different areas, but all of them will give you new frontiers, of nanoengineering at terahertz, all this high tech. So our guest host is Professor Gang Chen from MIT. Yeah, is going to introduce Evelyn later. So before we start the session, I'm going to, give you another advertisement is for after all these two super talks, we're going to have a Mind 2020 Young Scientist Award ceremony. In last 3 days, we have all these 54, young scientists, deliver the talks in Mind 2020. So all of them doing so good job, but who going to win the title? So we'll give you the answers and 10:30 the ICANX talks. So be sure to stay with us and to see who will be the winner and who is going to be the superstar in Young Scientist Award. So yeah, that's after this talks. So you will see all this. You don't move. You just stay with ICANX talks. You will see everything, all the surprise. Yeah. So without further ado, we're going to have our first speaker is Evelyn Wang. As I said, Professor Gang Chen will introduce Evelyn. So Gang, is your time and you chair for Evelyn's talk, please.
Good morning, good evening, good day. This is Gang Chen from Boston. Today, it's my great honor to introduce a superstar, Professor Evelyn Wang, who is also the head of MIT Department of Mechanical Engineering. She's my boss. Professor Wang is a Gale Kinder Professor in Mechanical Engineering, and she got her bachelor from MIT, master and PhD from Stanford, and she was a postdoc at Bell Lab for 1 year before she joined our department in 2007. Her research is in a micro nano heat transfer, and today you will hear her talking about a very important topic in energy and water. So I will just mention, I said she's a superstar. So let me just mention a few of her awards. She was a recipient of DARPA Young Faculty Award, Air Force Office of Scientific Research Young Investigator Award, Office of Naval Research Young Investigator Award, American Society of Mechanical Engineering Burgers and Rosenau Young Investigator Award. She is a super young star. And she was also named American Society of Mechanical Engineering Woman Engineering Award. And she was a recipient of ASME Gustus Nassen Award. And she was recognized as one of the foreign policies global rethinker in 2017. She's an ASME fellow. Without more, I can continue reading a lot of her award, but I will turn the stage to her and asking her to talk about this very important topics in energy and water. Evelyn, it's yours.
Thank you, Gong. Thank you for the really kind introduction. And thank you, Alice, for inviting me here today to share with you, with everyone here on this virtual meeting, our work. And first I wanted to mention, I feel great honor really to be introduced by Professor Chen. He's been a tremendous mentor of mine since even before I started at MIT as a faculty member. He certainly inspired me and given me so much in terms of support and actually new ideas. And I'll share a few of them that we've worked together on in the recent years. So I feel very honored to have him here to introduce me. I also wanted to mention that I know this is certainly a challenging time for all of us. And in these times, I think this is where science and engineering become so critical. And this is my hope, is that that you see that as an opportunity to inspire all of you to pursue these fields, because this is where we need to help make an impact and help make a better world. In fact, that is where I've directed my research a lot of my recent years, in these areas of thinking about climate change. Because while we know the coronavirus is right now, climate change is actually not that, it's already happening. And that if we don't address it now, we will be in trouble, perhaps significantly worse than what we're seeing today with the coronavirus. So while my research is only a little part, I think, of the picture, I hope that this may help you think about how you might be able to also contribute towards our mission to make a better world. And finally, I thought I'd just share that I'm trained as a mechanical engineer. And as you see from my talk today, that a lot of our research takes advantage of new materials that are developed such that we can engineer them into devices and systems such that we can make impacts in the areas of energy and water. And I'll share with you a little bit of the unpredictable path we've taken, in the sense that often when you do research, there's always a discovery element. But if you have a strong fundamental training in the areas, you can perhaps pivot, which is a lot of my students have done, right? To be able to now start to work on new devices and systems. And in fact, that's how we started working in a lot of the water space. So hopefully I'll share a little bit of that as I share with you some of the work that we've done. And these are really just snapshots that hopefully will give you a sense of the breadth of types of problems that we're interested in pursuing. So what I show you here in this first slide is the world total energy consumption. And in the terms of thinking about the distribution of energy sources that we rely on, and you can see that in fact, a primary component is still a significant reliance on petroleum or oil and natural gas. And the footprint, or in the amount that's actually being used for using renewables, is still significantly small. Well, you may ask, well, you likely know, in fact, well, what do we use these energy sources for? And it's really for the comfort often of our daily lives, right? So a significant portion of this is used for residential and commercial buildings, such as that for heating and cooling, especially in the hot summer days, or use of appliances. That for transportation, to get us from place to place, or also in the air as we fly across the world, as well as that of chemical industrial processes. And so when we think about this picture, I think the opportunity is that we need to develop new technologies that can help us mitigate climate change, which is a result a lot of what we're doing and using for the comfort of ourselves. Of course, another very important problem that is coupled to this, in fact, is thinking about the problem of water scarcity, which is also accentuated by climate change. What I show you here is a world map looking at water scarcity around the world and how many places in the world have water scarcity almost 100% of the year. And you can see this is also a very gloomy picture, in the sense that not everyone has access to clean drinking water. And in fact, one may argue that water needs may be more even critical than that of energy for survival. So we have been very interested also and motivated by this, looking at this picture, and the fact that certainly this is also a significant challenge that we have to think about, and it's highly coupled to the energy landscape. So I just show you here an example of that. For example, when we think about the power plant that we need for power generation right now, in fact, this is a picture just of the US. But in fact, these thermoelectric power plants withdraw about 40% of our US, of fresh water in the US. And so you can see that, in fact, the amount of water that's used such that we can cool the power plants is significant. And so there is an important intersection in thinking about energy and water. This is where I think there are significant opportunities for new technologies and the opportunities that advanced materials and nanotechnology has brought in the recent decades. And the fact these engineered materials has enabled us to now create new and enhanced functionality for all sorts of different applications. For example, you can now have new material properties, whether they're electrical, mechanical, or thermal. You can manipulate light in new and interesting ways. You can change how wetting of droplets kind of form on surfaces, or can we prevent fouling resistance using these kinds of structures? We can think about how we can develop methods using these materials for CO2 capture or energy conversion and storage, and the list goes on and on. So really the reality is that now we have all sorts of varieties of materials that we can work with, thanks to a lot of the chemists and material scientists has enabled this. But as an engineer, we think about it is how we get these kinds of materials into systems now with enhanced performance, such that we can address all of the challenges related to energy and water. So what I think about is while these often materials are tailored at the kind of nano and micro scales, there is an opportunity now to think about systems that are much larger than that. But as I mentioned already, that it's not just about the materials, because you have to engineer the system. And I believe that the strengths of my research group has been being able to now take these materials and actually engineer them using the analytical models and tools, simulation tools that we have, such that we can make more efficient, say, water systems or energy conversion systems. So what I'll do today is share with you just a few examples of the problems we've been working on at this intersection, where we can actually now take advantage of all these wonderful materials that have been engineered in recent years, such that we can now start to actually utilize them and incorporate them in important ways, and where we build on the models to actually create these high performance devices. Another emphasis of our work, which I'll show you today, is the fact that, as I motivated earlier, is that the renewable sector, in terms of how much energy is used right now, consumed via renewables, is still very low. We believe that solar energy is still a very powerful resource for us compared to all of the other energy reserves that exist, as highlighted by this graph. And so we'd like to think about how we can develop more efficient and lower cost solutions to make solar energy utilization even more viable. So with that, I thought I'd start off in talking a little bit about solar thermal power generation. Many of you may be already aware of this type of system that I show in this image. This is the parabolic trough concentrating solar thermal power generation system, by which you now utilize the sunlight and via the trough that you can see here to concentrate the sunlight in the form of heat that drives now the pump, drives, or I should say, heats up a fluid in this pipe that then drives the steam cycle. And this is now more of the readily deployed technologies. However, it's still very highly costly. So the opportunity is not only to improve efficiency, but also is to reduce costs of these systems. When we zoom into this picture of a solar thermal power plant, like what I showed you with a parabolic trough system, when you think about kind of the conversion from solar to thermal, typically on the order about 55% efficient. And when you convert from the thermal to electrical using a power cycle, a steam cycle, in fact, it's about 25% efficient. So the total efficiency of these systems are reasonably low. They're about 10 to 15%. And that poses challenges when you think about the deployment of these systems in terms of also how much it costs as well. So you can see here that, of course, steam cycles have been around a long time, and I won't focus too much about it, but I'll share with you just a snapshot of the kinds of things that we're doing that are more fundamental, that we think have more relevance, important relevance in terms of improving the efficiency here. And in particular, I showed this graph on the left and shows that there are important opportunities to be able to now increase the net efficiency of the steam cycle, this power plant, by decreasing the steam condensation temperature, and the turbine back pressure increases the net efficiency in the system. So we've been focused a lot on phase change, in fact, because this kind of cycle relies on liquid to vapor phase change. And in fact, a significant opportunity is how to enhance the phase change process, in particular, the condensation process, such that we can now potentially increase the efficiency. So our group has focused a lot on enhancing phase change heat transfer for some time. And while I will not focus on this, in fact, it's been the bread and butter of my group since I started, since my PhD was also focused on phase change. So I'm still pursuing it, but I would say more of the opportunities has been posed by engineering the surface, by using novel structures, such as examples, what you've shown in the middle here, to harness new behavior of phase change, such that we can enhance condensation processes, efficiency, and potentially incorporate these into these power cycles. I just show you a few snapshots showing some nice images, I would say, of phase change when you now have these engineered materials, such as what you see in the middle, where now you have droplets, instead of shedding via gravity at very large length scales, typically on the order of a few millimeters, you have very small droplets now that shed off because of the coalescence of droplets that now eject because of the super hydrophobic surfaces that we've created on these pipes. Now we've been able to now also not only kind of rely on a combination of surface coatings and these kinds of structures to harness kind of enhanced condensation behavior, but what I show you on the right is some of our more recent work by which now we can rely just on structure. And even in the case when you have condensation on these structures, that you can maintain a non-wetting type droplets that can roll off via gravity. And this presents also opportunities for more robust kind of concepts that don't rely on the chemistries themselves. So if you're interested, of course, you can read more about it, but I thought that I would now switch over and talk about the other side, which is on the collection side. And as I mentioned, this is, I would say that concentrators are typically quite expensive, and we think about these kind of solar thermal power generation systems. So an opportunity is rethinking ways for us to be able to now collect the sunlight in a more effective way. And this is where a project I've been working on for some time with Gong, Professor Chen, on using aerogels as a way to create more efficient solar thermal receiver designs at lower cost. So this has been a collaborative project for about 4 years or so, with a collection of students in my group as well as his group. In fact, through Professor Chen's leadership, this is really how we were able to receive funding through a government agency called ARPA-E in the US, where it's focused on high impact, high risk problems for addressing energy. So here, the concept that we've been focused on is developing a new material. While you may be familiar with aerogels, which I'll talk about in the next slide, aerogels have been often used in, say, buildings for insulation because they're known for very high insulation properties. However, typically, they don't have the optical transparency that you want, such that you can imagine a configuration as I show here. So what I show you here is a concept that the idea is to develop a very high efficiently, such a lower cost, air stable solar thermal receiver design, by which you have black adsorbers, which allows us to now collect the sunlight in the form of heat to then again transfer the heat to a working fluid, such as the oil. The key here is, though, we want to minimize losses. And the way to do that, in fact, is to introduce this aerogel that can allow the sunlight to penetrate and hit and heat up these pipes effectively while minimizing the heat losses. And if we could do this effectively, we can imagine configurations as shown here, such as in interfacing with a lower cost, lower concentration type system, such as linear Fresnel. And I should mention the reason why we've been very interested in solar thermal as opposed to, say, photovoltaics is the opportunity for heat storage and dispatchability. So this is kind of the concept that we've been working on for some time. And it's heavily reliant on the material, right? Whether we can actually create a material that allows us to achieve this concept. And so this is where we've been developing these optically transparent, thermally insulating silicate aerogels. As I alluded to already, typically these kind of silicate aerogels have a bluish tinge because of the scattering that you see and the non-uniform pore sizes that are typically created through the synthesis process. However, what we've been focused on is figuring out how to tailor these kinds of materials such that we can now get higher even solar transmittance as glass, which is what you see here, comparison between our aerogels and commercial aerogels and that of glass. You can see a picture of this. You can see what this looks like in terms of soda lime glass and what we've been able to achieve with our aerogels. And so by being able to tailor the particle size such that we can minimize scattering, we can achieve a material that has still very low thermal conductivity to minimize those losses, those thermal losses I mentioned, and also still achieve high performance at high temperatures around 400 degrees Celsius. And so once we've developed this material, our first step was to look at just characterizing this material and the opportunities that it presents. So one of my students, Lynn, with a collaboration, of course, with the whole group, developed a test by which he introduced this low scattering aerogel into a simple setup by which you have a black body absorber, and you now introduce the solar radiation from the top, and you do some simple measurements. And it is non-vacuum in this case, so you don't require vacuum now because of the fact that you have this low scattering aerogel in its place. And what we show here is that when we do measurements, this is now in a lab experiment. You can see this is a temperature response as you introduce the solar radiation as a function of time. And this is an ambient temperature with about a 20 millimeter thick aerogel. You can see that, in fact, the absorber now reaches temperatures over about 240 degrees. Now, of course, as you increase the thickness, you expect that the performance to be even better. So the stagnation temperature is shown as a function of the thickness. And we've been able to reach under one sun, so no concentration and without a vacuum or selective surface, a record high stagnation temperature because of the presence now of our aerogel that we've created. This has been exciting because of the opportunities it presents, not only for solar thermal type power generation systems, but also potentially using this kind of heat now for industrial processes as well. This is done in the lab. And what we did is our next experiment was on a rooftop of MIT, as you see here, where you can see that this was done in a hot, or I would say sunny winter day, where the ambient temperature is less than about 1 degree Celsius. And you can see that even in these very cold conditions, once we introduced the sunlight outside to this absorber, in fact, you can see that the absorber has reached over 220 degrees or so. So this certainly shows this significance of just how we can take advantage of the material in a way to now get high temperature surfaces. Of course, our setup was, as I showed you earlier, really kind of the conception of this project was thinking about how we might be able to use this for a solar thermal kind of concentrating system for power generation. And so what we have done through these years of effort, in fact, has been able to now build a prototype, which you see here, which is about 1 meter long, tiled with these aerogels, which were done because of limitations of what we can do in terms of scalability. And now show that we've been able to build a system with this type of receiver with interfaced with a linear Fresnel array. Like I said, this was like a multi-year effort to actually build the system, which has turned out to be much more challenging than the really conceptual aspects of it. And show that, in fact, this kind of aerogel receiver can have significantly higher performance than that when you don't have an aerogel in this case. And so we've been excited about this as one potential pathway. Of course, one of the challenges we face is to realize this kind of system is scaling the materials. As I mentioned, we tiled them. And so this is something that we've been pursuing, actually, as I'll talk about next, is a student of mine has decided that she wants to spin out a company focused on this. But in fact, it pivoted also as an interesting opportunity where once we've developed this material, there are also other applications that can actually be enabled. And one of them, as you can see here, is highlighted in this image, by which you can see that because of this excellent transparency, or in the Windows world, the seeking of clarity, in fact, of the window. This is where my student has been interested in now pursuing the Windows market with this technology. And so Elise now has also done some work in looking at how you can create these kind of high transmittance and low haze type aerogels, which becomes the metrics which become important to start to realize to create double pane windows that can be significantly higher performance in, say, a typical kind of double pane windows, or it can compete with triple pane type performance for the double pane type price. And so she just recently launched AeroShield and is looking at how we can scale up these materials such they become commercially viable. So through this path, I should mention then what has happened is inspired another one of my students, Arnie, to look at other types of aerogel structures. And in fact, in this case, he's been looking at material called polyethylene for another application related to passive radiative cooling. So when we think about the Earth's energy balance, the reason that the Earth just doesn't continue to heat up, and in fact, there is infrared emission towards space, right? And it turns out the reason that happens is because there is an overlap between the black body emission spectrum and the atmospheric window that allows radiative cooling on the Earth. And so this has been a very interesting area by which there's been a lot of interest in recent years by being able to take advantage of this kind of atmospheric window in the ranges of 8 to 13 microns, such that you can actually use radiative cooling to reject heat from various objects on Earth. We've been interested in the area of daytime radiative cooling, where the idea here is that now the challenge is not only instead of at nighttime, daytime you also have to deal with the sun, right? And the idea of daytime radiative cooling is that you can actually try to achieve temperatures below the ambient. However, this has typically been done using optically selective surfaces by which you have high solar reflectivity and high infrared emissivity, or geometries such as what's shown here on the bottom. But when you look at the performance with looking at cooling power and the emitter subcooling, how much temperature you get below zero, a lot of the past work is focused in this region in the green here. And there's still a significant opportunity now to push towards lower temperatures as well as higher cooling powers here in this space here. So an opportunity arose from my group in thinking about the expertise we've had with aerogels, I will say, and thinking about how we could potentially develop material now that can now allow us to now still have high reflectance or even improved reflectance such that we can start to access more of this space and also have excellent thermal insulation in the process. And as I mentioned already with aerogels, they're typically known to have very good thermal insulators. Now the question becomes, how do we get this high reflectance in the solar spectrum? And this is where we've been focused on using material using with polyethylene as the aerogel material. And you can see here that polyethylene now has a reasonably low density, has a relatively low conductivity, and its spectral characteristics are shown here, such that it's very highly solar reflecting and it's IR transparent. You see this clearly from this nice depiction on the bottom where there is MIT. So you can see that now in the solar wavelengths, you see a white type material. However, in the infrared, using infrared camera, now you can see this MIT. This is work done, as I mentioned, with my student right now, Arnie, where he has now taken this material and tested its performance. And one of the opportunities with a collaboration is that we've been able to take this material and this test setup to San Pedro de Atacama in Chile, which has an altitude about 2,500 meters. And the reason we chose this location is that it has a low humidity, which means it's more transparent. It could have better performance for the mid-IR radiation. And it has high solar irradiance, right, in this region, which makes it one of the most challenging places for daytime radiative cooling. And we wanted to test out whether these kinds of materials would be, in fact, effective. And so, in fact, with a setup where we basically have two, I should step back and say we have two devices. One basically has a device by which you place the aerogel on top, and one without an aerogel. That's the difference. You can see that there is significantly different performance. In fact, using this polyethylene aerogel, we were able to achieve stagnation temperatures about 13 degrees Celsius during the day, compared to say 1.7 degrees with only this emitter itself. And we've also been able to achieve higher cooling powers as well at sub-ambient temperatures. So this presents interesting opportunities because radiative cooling is a passive technique by which you can imagine now, and reasonably you can think about how you can potentially make it low cost enough for, say, developing world applications as well, by which we can now use this for refrigeration of food produce, or also in thinking even about building cooling and how we can now reduce the loads in air conditioning units using this kind of passive approach. So I thought I'd give you this example just as some kind of direction that we pursued from developing expertise in aerogels. Now I thought I'd switch gears a little bit as I motivated this talk in terms of kind of the various places by which we take advantage of our energy sources and consume it. I thought I'd share with you now a little bit about what we've been thinking about in transportation. And in particular, how do we minimize greenhouse gases through increased deployment of electric vehicles? And I will say one of the biggest challenges with electric vehicles is driving range. And this is a project that we started about 5 years ago or so. And this is also in collaboration with Professor Chen, Omar Yagi, and Carlos Hidrovo, by which we were also funded by RPE to think about new thermal batteries for electric vehicles. One of the biggest challenges, as I mentioned already, is that driving range is what limits the deployment of electric vehicles. And in fact, one of the things that dictate driving range is your HVAC system. So in fact, it can decrease your driving range by up to about 40%, as shown here. And so what we sought to do is develop a new HVAC system, which is called a thermal battery. And the reason it's called a thermal battery is that instead of relying on your electrical battery to heat and cool your cabin, you're actually now charging it before you drive, such that it doesn't rely on electric battery power to now provide the heating and cooling that you need for your comfort. So that's been the concept that we worked on. And this is what I show you here, is that we were tapped based on what RPE sought out to fund us for, is to in fact create something that's very compact, lightweight, and still have reasonably high heating and cooling capacities, because it would only make sense if it could compete with that of what electrical battery can do when driving a typical HVAC system in your vehicle. And this is where we came up with an idea that relies on the concept of adsorption. The idea here is when you have a surface, such as shown here, and you have, say, a pool of water, that in fact, when you have a chemical potential difference between this dry, say, adsorbent or this solid surface, and your water, that in fact you can evaporate and it absorbs onto this surface, which now is exothermic and releases heat. Now you can also see that when you now desorb it, you in fact now use energy, it could be in the form of heat, to now release the water, and then you condense it, which is now an exothermic process. So the idea here is that we want to evaporate, and if you can evaporate, you cool, in fact, in that process, so that, in fact, you can get your heating and cooling streams from the adsorption process itself. Depending on where you channel, now provide heat exchange, I guess, to your system in this case. And this is really fundamentally what we've been using, in fact, in thinking about adsorption processes, not just for now this electric vehicle, but I'll show you later, water harvesting. And so this concept came out of this project by which we want to develop an adsorption-based heating and cooling system using this principle here as I show you. And the idea now is integrating it into a system concept. So now we have this reservoir, which is that of water, and we have an evaporator, an adsorbent bed, and a condenser. In the cooling mode, as I mentioned, what you're doing here is that you have an adsorbent that is dry. So there's a chemical potential difference between your wet reservoir and your adsorbent. And through the process, you evaporate. So when you're evaporating, you can in fact feed that cooling, right, that you get from the evaporation to now the EV cabin. Now in the heating mode, instead of taking it from the evaporator, you take it from your adsorbent bed. So once you now have those water molecules that adsorb onto your adsorbent, as I mentioned, this is exothermic. It now releases heat, and that can be delivered to your electric vehicle cabin. Of course, now how do you charge it? The way you would charge it is now you interface it with now the condenser, and now you apply heat to the system, and you can now release the water and now condense it, eventually put it back into your reservoir. So this is a concept by which you can take advantage of, and we've demonstrated it through the years. And what this is relied on is not only now these novel material sets, such as these really high capacity adsorbents, such as these zeolites and metal organic frameworks, which is kind of a new class of materials that have received a lot of interest in recent years. And also how we can now enhance the thermal properties and mechanical properties to realize this kind of stack design for a thermal battery and the optimization in the thermal engineering aspects. So through the combination of the materials and the thermal design, we've been able to achieve a system that seems to be readily now can be starting to think about how we might be able to actually incorporate it into an actual vehicle design. In fact, that's what we've been working with Ford for quite some years. And in fact, we're still working with them to now start to think about translation. And so I just show you a few images of a two-bed type design, such that this can facilitate even recharging during driving. And this is a test setup. You can see that it doesn't ever look that pretty in the lab, but I thought I'd show you this so you can get a sense of the scale of this kind of system that we've interfaced with the vehicle components in a typical electric vehicle, such that eventually we can think about how all this packs in to the design and ultimately demonstrate performance where we can achieve the heating and cooling that we've set out to. When we think about now this energy kind of storage mapping, we're getting to a place by which we can start to now kind of really compete with electrical batteries when interfaced with that vapor compression system, such that this becomes a more viable kind of technology. As I mentioned, this is something that we've been pursuing with Ford as a partner. And we think not only can this be applied in electric vehicles market, we think that this kind of concept of absorption that pushes kind of the performance of the materials and the systems design can be also used for HVAC, such as absorption-based heating and cooling systems as well. So this brings me to, I thought I mentioned just a couple more research projects. And this is, in fact, I share you the electric vehicle thermal battery work, because in fact, this is how we got into water harvesting. right? So it's kind of a meandering path, as I mentioned, is often you start to realize the opportunities that lay ahead are not just one direction. And in fact, this work has been in collaboration with Omar Yagi's group because of this work that we developed with electric vehicles. So when we think about the water in terms of how much there is actually in the air around us, in fact, equivalent to about 13,000 trillion liters. So there's a lot of water actually in the air. So when we think about kind of water scarcity maps, in fact, we think there is a significant opportunity here and being able to harness some of that water in the air for clean drinking water. And water harvesting has been known for some time. And I will say one of the most prevalent ones used right now is called dewing, which is very well suited for high humidity conditions. But you can see here that when the humidity starts to get low and the ambient temperatures also are low, then in fact, you start to see that there is a challenge with the efficiencies of these type of dewing systems, which essentially relies on condensation with a refrigeration type cycle to now get your water. So here we see the thermal efficiency as a function of relative humidity. And you start to see that in this regime here, that this type of dewing process, relying on the refrigeration, becomes infeasible when the humidity becomes low. And in fact, when the dew point becomes negative, you can imagine now the amount of energy needed to use to now to freeze the water becomes tremendous. And so there certainly are limitations to dewing. And this is where we think there is significant opportunity ahead by which we want to leverage now adsorption. And this just motivates, again, why this is important. Of course, you can see in the world that there are a lot of areas by which the global, in the map, that the relative humidity is usually lower than about 40% or so in the world. And so we think this is where we'd like to pursue. And what we've been looking at is a water harvesting technology by which you can start to extract water even in arid conditions, such as that in deserts. The concept here is very similar to what I just showed you in the previous section on thermal batteries. In fact, it relies on adsorption. And the idea here is that you have a material. In this case, we're using these metal organic frameworks, which I didn't touch upon in particular by the details, but they have very unique characteristics by which you can look at an isotherm, which is a water uptake as a function of the humidity. And the isotherm is a shape of this curve. You can see that the different isotherms can dictate what your water uptake is at what humidity conditions. And so the idea here is to incorporate these kinds of materials into, say, a layer here on top. At nighttime, you can, in fact, now capture this water from the moisture in the air, right, into this material that's originally dry. And during the daytime, that in fact, you can release the water, right, from the material itself and then condense it. So again, it's an absorption process, not used now for heating and cooling. However, those physics still exist. So you have to think about how you manage that in the system. But the idea here is now for water capture. And depending on what kinds of isotherms you have, in fact, you can imagine how you now tailor the kind of materials you need for particular conditions. And so that's how we started working in this area of water harvesting, which has been really exciting. And as I mentioned, a lot of it has been working with chemists, in this case with Omar Yagi's group, where we use MOF 801 as a proof of concept for this. And not only that, is now also doing computational models to help us now design the layer thickness so that we can get kinetics appropriately, so the time it takes in terms of how long it takes to absorb and desorb, and do the characterizations in the lab before we can start to actually develop prototypes. And so what we've shown is now a proof of concept water harvesting device where we used a single layer of this MOF 801, which is shown on here on top here, on the MIT rooftop, by which now we've demonstrated that in fact, with this kind of approach, you can start to create water droplets that are clean in nature to now harvest water. And this is a very first step proof of concept because the amount of water is small owing to the materials availability. But this suggests that there is a significant opportunity by which we take advantage of adsorption to now start to realize water harvesting devices. And in fact, we've been able to characterize it. So this is just showing the temperature to help us now also compare with our models that we developed. And you can see here that the condensation temperature by which we now can generate the water is above that of the ambient dew point. So we are not relying on the dewing as other previous technologies have done. We showed this initially at MIT, but what we wanted to show is that while dewing technologies are excellent at high humidities, when we now have low humidity conditions, we believe adsorption is one of the most viable approaches ahead. And so we brought our harvester with some improvements to an arid area of the US in Arizona. And the idea here is you can see that, in fact, in these kinds of conditions, dew point becomes negative, right? You can see the kind of nighttime and daytime swing of the relative humidity in green. And so this becomes a very challenging condition by which other kinds of technologies are infeasible. And so we wanted to demonstrate our prototype, which we made some improvements on. You can see that, in fact, I wanted to highlight this because we've been able to now introduce some of the things that we've looked at in other studies, such as that of our aerogel, to now maximize the solar amount of flux onto our device, as well as also using at nighttime radiative cooling, such that we can, in fact, now decrease the temperature to maximize the amount of adsorption on our surface. So we've done some kind of innovations in engineering thanks to some of the other things we've done in the lab. It's really the integration of various pursuits, I should say, that has enabled us to also improve the performance of our device, which is what I show you here. And I'll just show you a brief video of what it looks like on this device. And you can see that immediately fogs up because once you start to release the water molecules, and then it condenses everywhere essentially, and then starts to heat up everything and start to see the windows and the droplets that are forming through this system. We can also do similar characterizations. You can see here, temperature is a function of the time and what it looks like in terms of this particular device. And what we've been able to show is that we can say, achieve about 0.3 liters per kilogram of the material. And that's highly dependent, of course, on the isotherm of the material by which we can, what's the maximum uptake of the material itself. And certainly there's a lot of room for improvement in terms of also not only the materials, but also scalability, such that we can start to realize high performing, larger scale systems by which maybe we can use them for remote areas and for families. And lastly, before I conclude, I thought I'd share with you another just recent project that's more focused on thermal engineering. And this is also kind of inspired by just various aspects of work in our lab, by which we've been able to now think about how we can achieve higher performance or higher efficiency solar stills for water desalination. And this is work in collaboration with Evelyn Wang's group and John Leonhardt's group, and led by a lot of my students and postdocs. And so certainly when we think about water, we talked about water harvesting. Another very abundant area of research is that in water desalination, where in large scale systems, reverse osmosis is kind of the main technology that people use. There's been a lot of interest in recent years, though, for kind of remote compact units, such as what I show here. In fact, Professor Chen's group has been a leader in this area and introducing ideas such as kind of local heat localization using novel structures, such as carbon foams, by which you can start to now kind of heat up locally the interface, the liquid vapor interface, such that you can produce very efficient processes there. Also, there's been demonstrations of these kind of solar stills that are placed in salty ponds, by which, in fact, you can achieve high performance and in a passive way. We've been kind of building on a lot of these studies to think about where are the opportunities, because certainly this has received a lot of interest and its importance given the amount of kind of salty streams and water reservoirs that exist in the world. However, there are still kind of opportunities ahead, and that's where we try to focus on in terms of the challenges still with water production being relatively low because of various transport resistances and the vapor kind of enthalpy that is lost to the ambient that's typically happens in these configurations, as well as the low flexibility of the materials choices, because often they need to have a lot of different couplings of high spectral absorbance or selective spectral absorbance, wickability because you're drawing liquid, and high thermal insulation typically coupled all together with the material. And so what we've seen is an opportunity to maybe think about how we can create a more efficient system, really thinking about systems design. And one of the key aspects is, can we now think about these kind of solar still type configurations by decoupling the functionalities of the solar absorption, the thermal insulation, and the water transport? So the idea here is that now we have a configuration by which now we place this solar still, and we have now excellent insulating. We actually, in fact, use our aerogels here to interface it with an excellent solar absorber. And now we have a wick that's low cost in nature that now drives the brine up and now allows us to desalinate and then effectively evaporates because of heat being interfaced to this low cost evaporated wick, by which now you can condense on a metal surface. And in fact, the second aspect is not only just having a single stage, but to have multiple stages by which you can recycle the vaporization enthalpy to drive evaporation in the next stage to achieve much higher efficiency in this process. So that's the idea here. And in fact, we've been able to design a system. While I'm not showing all the details, in fact, of the modeling efforts, we've been able to design a system with these low cost type components. Here's a solar absorber with a multi-stage stack of about 10 of these layers. You can see here, in fact, we just use a paper towel as a wick. So it comes a very low cost type system. And we use aluminum plates as our condensers that are hydrophobicized, you can see here, such that it can shed off the water easily. And so with this type of configuration, with these really low cost type components, we've been able to do kind of lab level testing by which we interface it again with a solar simulator. We can look at the amount of vapor flux generated at each stage. And you can see that as you increase the number of stages, there is kind of decrease in terms of amount of vapor that's generated, because also obviously at some point you start to now degrade the performance because of the heat that you have from the previous stage is lower, right? The amount of so in this case, in fact, we've been able to characterize these kinds of systems and show that we can, of course, expect a much higher efficiency, about 5 times improvement to that of a single stage type device using this configuration. And what was exciting about this is because of the thermal engineering that we've been able to do with these low cost materials, we've been able to now access a regime much higher in terms of efficiencies and production rights compared to previous papers. So we also done some outdoor experiments with this, and we've shown that through the outdoor experiments, in fact, we have excellent performance as well, where we've been able to get a productivity about 2.6 liters per kilowatt hour. And it has implications as to how potentially you might be able to incorporate these really in thinking about now scaling up these designs for use in a passive way for a lot of remote regions with access to salty streams. I'll show you just a brief video here of the collection. So this was done on the rooftop. You can see here that over time, you can start to see with this graduated cylinder in this setup that we start to accumulate the water through this process of evaporation condensation with this multi-stage solar still. Okay, so I know I went through quite a bit of material, but I think that the focus of this talk is really to highlight really some of the opportunities and maybe the path that has led to these opportunities in developing new energy and water technologies. And I showed you this graph earlier, is that certainly there are significant opportunities ahead. And think about how these engineered materials and innovations at the nanoscale can be applied to various systems that can have impact in the energy and water landscape. That includes, of course, now a need to think about scale up of a lot of materials. I showed you some innovations that enable prototype designs, but to make them practical, we have to think about how do we actually effectively scale up at a sufficient cost or low enough cost that it becomes available or can be possible in the market. There's a robustness aspect also of the materials that become really important in terms of its reliability. And of course, as I mentioned, the coupling between the novel materials and the device engineering becomes really critical, such that we can really realize performance that we seek. And there are abundant opportunities ahead. As I started my talk, I mentioned that I think it is really up to us to really set kind of the future in terms of how do we mitigate climate change? How do we address these issues associated with energy and water, so that we can make our world, a better place. So with that, what I showed you today, of course, is done really by all my great grad students and postdocs. And I've been really fortunate to have amazing, creative, intelligent, and just driven people in my lab for so many years. And so I wanted to, of course, acknowledge them in this. I've been also fortunate to have just really incredible collaborators. I mentioned Professor Chen has been one that's been a tremendous support of mine for many years, as well as others here, as well as the funding that has really enabled us to really pursue a lot of our kind of ideas and really to reach kind of directions that we didn't anticipate before. So thank you very much. And I look forward to hearing your questions. Thanks.
Thank you, Evelyn. That's a really amazing talk. Although I know your work, but hearing it and really I'm inspired. And there are a lot of questions. So before we take the audience question, I'll take advantage of me being the chair and ask you 2 questions. And
Sure.
I'll put them together. So this is rather than scientific question, I'll just put it into, as Alice mentioned at the beginning, today we have 2 powerful women speakers. So I'll ask you the question about the female in science and engineering. And one would like to ask you, really you're not leading the, I'm in the same department, so I'll say the best mechanical engineering department in the world. And as a woman in doing research and leading, what do you see are the challenges? And also, I want to ask you the question. I know MIT Mechanical Engineering Department has 50% of our undergraduate students are females. So I would like to ask, whether you have any insights, how we could attract so many female students to mechanical engineering. You can choose whatever.
Great, thanks, Gong. Thanks for the questions. I'll try my best. Tough questions. So certainly, I think I've had a lot of great privilege in the recent years to take on this role as department head. And I think I will say that I've been fortunate, as many of you know, Professor Gong Chen was the department head before me. And I think a lot of the, he really set a lot of the framework for me to take on the department and for us to continue to lead in this area. I will say, when you think about, and I think I will say that MIT, I will say that has been a tremendous place, and maybe this answers both questions a little bit, is that I will say that the environment there is extremely collaborative. And it's all the way stemming from students. I was a student there in the late 90s. And to now, I think everyone just works so collaboratively, and there's so much support around you that while it's a tough place and expectations are high, it's the collaborations and really the support that you get that make a lot of the challenge seem surmountable. And I will say that in thinking about mechanical engineering, I think often people think that it's a very male-dominated field. But as Gong said already, that we're at 50% undergraduate women. And I will say that I think there are many reasons for this. And I think it's been a result of many years, decades of hard work, right? When I was an undergrad, we were probably about 30% women at that time. So it has changed a lot, even in 20 years. And I will say there are a lot of efforts. It's not just starting at MIT, but the pipeline. So how do we encourage females to want to pursue engineering? I will say mechanical engineering in particular was exciting to me because I could see that there was an element of design and the potential for making global change, that the kind of the opportunities that mechanical engineering presents, because it's a broad training to allow you to really understand a lot of different concepts and bridge them together to really create devices. And if you're interested in kind of helping save the world, I think we see a lot of our undergrads interested in that this is a really exciting discipline to be in, because there's so much it can do from the fundamentals to that of device design, right? So it's not just from the starting. I would say that, you know, a lot of this starts from even before MIT and increasing the pipeline. We have a program called WTP, Women Technology Program, where we invite women in high school to come visit us during summers, to be able to be exposed to engineering and what mechanical engineering is. And it's a hands-on program with a group of female students and instructors. And we believe that a lot of them get very excited about engineering as a path, right? And they see what mechies do, not what their conception of what mechie is. And I think that encourages hopefully encourages a select group of students, female students, to want to pursue mechanical engineering. I will say, when I was a student, we had one female faculty member. That was Mary Boyce, who is now the Dean of Columbia. And of course, we all kind of looked up to her, but we've increased the number of female faculty in our department tremendously. In terms of tenure, we can say it's a 6x increase since the 2000s. And actually, a lot of this has to do with Gong, Professor Chen, who has hired so many female faculty and helped them get through the tenure process, including myself, I will say. So I will say having female role models has been really important. And of course, we're not there in terms of numbers yet. And we are committed to that, of course, as well. But I think as you see more examples of successful women, there is an opportunity to hopefully bring in more. And I will say that finally, I know I keep on talking now, but I will say finally, I think the reason I took on this job, so Professor Chen spent some time convincing me about taking on this role. And I will say that the reason I agreed at the end with 2 young kids right now is that there is a significant opportunity, not to serve as a role model per se, but to actually help make change and impact. And potentially that's larger than maybe what I could do now in my research. And that's the kind of the breadth of impact. And I think this is actually what Professor Chen told me, is that, you know, the breadth of impact is just tremendous. And I think that is something I think we're really tapped to do in life, right? Finally, I'll say I always tell my students this, and I think we think about it in this way, that, you know, especially when we're privileged to be a place like MIT, that we have a responsibility, that if we're here, that we are training leaders, and we want our leaders to go out there and also help shape the world so that it is a better place. And I believe that hopefully my role now can help that also in an important way. So I know that was a long-winded answer, but hopefully that touches on some of the questions that Professor Chen just asked.
Well, thank you very much, and you are so humble in saying about me. As a faculty member, I really admire what you've been doing for the department. But I know audience has a lot of questions, so let me turn attention to questions from audience. The first question is, dear Professor Wang, for harvesting the evaporation water, if applied in the ambient, how to solve the problem for stability?
I think I'll try to answer the question in terms of stability of the material or stability of the device. So stability of the material is dictated by the chemistry. I will say that when we think about these materials for water harvesting, that's one of the first criteria in terms of working with materials that are stable. The second is about maybe evaporation. And the way this works is that, which I may not have explained clearly, is that it's in a chamber, right? So when you're now exposing the environment to the material, you open up the chamber so that you can absorb the material. However, when you're now releasing the water from the material, you have to close the chamber so that it doesn't get escaped into the environment, because then it wouldn't work, right? So you have to close the chamber and you have to confine it in a way. And in fact, that's the key step. Otherwise, you're essentially what you're doing is creating a local environment that has high humidity. So then you can condense near ambient in that process, right? If you don't do that, then this whole absorption process would not be effective. So the key is really closing the chamber and being able to now locally create an effective humidity that's high, such that you can now not require a doing type cycle to now condense the water.
Probably the question also has about what about the variation of the environment, the humidity variation that might be part of the, I don't know exactly question.
Sure. So the variation, so I think it depends on your isotherm, right? So if depending on the environment that you'll have to choose an isotherm that can work. Usually it's the low humidity conditions that are very challenging, and you could do, you can basically capture anything then at higher humidities. So you want to work with the worst humidity condition as possible, and then use that material for everything else, right? So that's kind of how we think about it. Of course, there could be other configurations that we have not explored, and it really depends on the size, weight, costing requirements. You can imagine having a system that has multiple types of adsorbents in the system as well, right? But I think it really depends, and that's something that I think is tailored depending on the place and maybe the application at hand.
Great. So the second question actually was related to from a female PhD student. So the question is, Dr. Wang, I'm a female PhD student, now is struggling with my research and life. It's a really hard time for me to balance this. Could you tell me how you handle this?
That's a great question. I will say that I think life is not about balance. I think it's hard to balance things in general. Right now, I would say that, but it's about passion and maybe just being able to just work with it and not think about it too much. That's all. I've come to this recent perspective because I get that question a lot about balance. And, you know, I right now have 2 kids, they're 4 and 2. When I took on this job, my son was 6 months, but Gong encouraged me to do it anyway. My research group has shrunk a little bit because of this as well, because I don't have time to write grants as much. And this job as department head takes more than, I think, 100% of your time. So if people ask me, how do I balance? And I say, I don't. And I think a lot of things do fall by the wayside. And I think at the end, it's about just making sure the things that you're doing, you do as good of a job as possible, right? At that moment in time. So for example, if I'm focused on something related to our apartment, I just focus on that. And I know my children are there, and right now in coronavirus, you hear them in the background sometimes on these Zoom calls. But I think the focus becomes very important. And when you're doing research, the best part about being a PhD student is being able to focus on something 100%. And that's something I miss, because now you get distracted by a new email that's urgent, something else that's urgent. And that's something that you have to savor as a PhD student. And I will say, though, you're never alone. I definitely could not do this without the support of my wonderful husband, who takes care of the kids a lot, support in terms of the faculty like Gong and others in our department who have just been tremendous supports. And I have, so it's about building people around you and creating a community that can help you through the challenges. And I think a PhD is very similar to that. I think often PhDs, there's never an easy PhD. And in fact, I think if you had an easy PhD, something probably is wrong, right? Most people have a challenging time during your PhD for some reason or another. And it's about getting through it. It's about getting through that challenging time and being able, it's not about being alone in it. It's about getting through it with people around you. And if you need the help, you should seek it, whether it's your faculty, your advisor, other faculty, your students, postdocs, your family. I think that's one thing to think about, because I know I couldn't have done it alone. I still can't do it alone. And so I think if you can reach out to those resources and also try to just appreciate what you have the capability to do, maybe that can help a little bit as you kind of go through your journey as a PhD student. And it's actually a life journey, I would say. I think PhDs, it's great when you go through challenges during your PhD, because you're protected in a lot of ways during that time. Once you enter the real world, it's different. So it's almost like a good trial run. And thinking about it like that as to how you access resources. A PhD is about problem solving. It's about how do you actually kind of solve this problem, and the answer is not obvious, right? And otherwise, you would have had your PhD. Actually, my own advisor, when I was at Stanford, told me this. I used to be worried about my PhD and saying, what's my thesis? What's my thesis? And this is Professor Tom Kenny. He would say, oh, Evelyn, don't worry. Once you know what the title of your thesis is, you're done. Or what the answer is, you're done. So that's the way to think about it. And it's about kind of enjoying the days. And while it's hard, still understanding what you're there for, and kind of embracing the challenge and knowing that you will get through it, and you don't have to do that alone.
Wonderful, Evelyn, for sharing that.
You typed that twice. You got wrong one. Okay. So sorry. Okay.
Okay. Our next question.
Gang, we made some mistake. I posted the wrong one. Okay. Yeah, I can read that one. Okay, Evelyn. Yeah, sorry. Yeah, I just copy post a wrong one. Yeah, this question is for Professor Wang. Amazing work. As you mentioned, your device already used in the desert. What packaging strategy you use? Yeah, for the device you use in the desert one. Yeah,
the packaging strategy.
Yes.
That's a good question. So I will say that these are all proof of concept prototypes. They are not products yet. I will say that a lot of them, so they rely on just various materials that we've, off the shelf type materials that we machine in the lab. Often they will have kind of various metal structures, aluminum, for example, copper, acrylic, even, those kinds of materials to be able to create them. So it's pretty off the shelf kind of prototyping materials. I will say that this is not kind of a translation project yet. And I think there's still a lot of room to get us there to commercialization, so that we can start to consider actually the cost of materials and how that impacts our prototypes and eventually actually a device.
Okay, really great. Thank you all of you. Gang did a wonderful job and Evelyn answered so many questions. I especially love the part answer for how to balance the life for, your PhD that because many of the young students now is really worried more about, how they can get through all this. Like you say that just enjoy, hard working and then the result is there. So you can easily to get, the title of your thesis, that type you win. Okay, Evelyn, this as normal I can ask tax. So we give you one, certification for your wonderful talk. Yeah, as you connect the world and the universe. So Evelyn, that's all for you. Okay, thank you so much.
Thank you.
Yeah, very great. So our next speaker is Mona. We move on. Thank you, Evelyn, and